A hydrogen sky and an endless ocean. Would you survive here? If you could teleport to K218b right now, under a dim red sun and a hydrogen-rich sky, would you actually be able to live there? Or even survive the first few minutes? There are few questions more unsettling when we think about our future in the universe. We like to imagine that if we ever visit another world, it will feel at least a little bit like home. Blue sky, solid ground, a familiar pull of gravity. But what if the first truly life-friendly planet we find is nothing like Earth at all? In the hunt for alien life, we have placed a lot of faith in Earth-like twins, rocky planets, shallow oceans, thin atmospheres. After all, life arose here. So it should be noted that our entire strategy has been built around the idea that copying Earth is the safest bet. But K218b challenges that idea from the very start. This planet orbits a cool red dwarf star about 124 light-years away in Leo, sitting in its Goldilocks zone, where temperatures could, in principle, allow liquid water. Yet K218b is no simple Earth cousin. It is larger, about 2.5 times Earth's radius, and several times more massive, a swollen mini-Neptune rather than a rocky twin. This means its gravity would feel crushing to us, its atmosphere much thicker, its entire personality profoundly alien. Imagine arriving there. The sky is not blue, but a hazy, muted red, filtered through a deep hydrogen envelope. Daylight feels like an endless twilight, more sunset than noon. You look for land, for mountains, for any coastline. Instead, you see only a dark, rolling ocean stretching in every direction. No continents, no islands, just a global sea wrapped in clouds. Would you feel awe or pure panic? So let's begin with what we actually know. Using the James Webb Space Telescope, astronomers have dissected the atmosphere of K218b. In the passing starlight, they have found water vapor, methane, and carbon dioxide, the chemical fingerprints of a hydrogen-rich sky hovering over a possible deep ocean. There are even tentative hints of a molecule that on Earth is mainly produced by marine life. Optimistically speaking, this might be the first real example of a so-called Hycean world, a planet with a hydrogen atmosphere and an ocean that could, in theory, be habitable. So it's time to find out the truth, because the real question is no longer just, is there life out there? It is, what would life actually feel like on a world like this? Physically, under that heavy sky. Biologically, in that endless sea, and even psychologically, for any alien ecosystems, for possible civilizations, and for us, if we ever dare to visit a planet where there may be life, but almost nothing feels like Earth. And if we did step through that teleporter, would K218b welcome us, or erase us in moments? Why this strange world might matter more than an Earth twin. And that is exactly why this strange planet might matter more than a perfect Earth twin. In the hunt for alien life, we usually picture a blue marble. Solid ground, thin nitrogen atmosphere, familiar gravity. We build our instruments, our models, even our hopes around worlds that look like home. But while Earth-like planets grab the headlines, they are not what the universe mostly makes. Statistically, the most common type of planet we see out there is not a rocky Earth, but something in between Earth and Neptune, sub-Neptunes, mini-Neptunes, bloated, mysterious worlds like K218b. It should be noted that this is not a small detail. If life needs a rocky surface and a gentle, Earth-like atmosphere, then only a narrow slice of planets in any star system really counts as habitable. But if life can adapt to a Hycean world, an ocean planet wrapped in a hydrogen-rich atmosphere, then everything changes. This means that suddenly, not tens of billions, but perhaps trillions of planets in our galaxy alone could support oceans, chemistry, and maybe biology. So let's begin to see why K218b has become the poster child for this idea. It orbits a red dwarf star about 124 light-years away in Leo, sitting in the Goldilocks zone, where starlight should allow liquid water. Its mass and radius put it firmly in that sub-Neptune category. Too big to be a simple rocky world, too small to be a classic gas giant. For years, that made it scientifically interesting, but philosophically awkward. Where would life even live on a world like this? JWST changed that. With its infrared eyes, we can watch starlight filter through K218b's atmosphere as it passes in front of its star. From those faint fingerprints, Webb has revealed water vapor, methane, and carbon dioxide in a hydrogen-rich envelope. Optimistically speaking, that is exactly the kind of mixture we might expect above a deep global ocean. Some analyses even hint at dimethyl sulfide, a gas on Earth mostly produced by marine life, though that claim is very tentative. But while the data are thrilling, they are also deeply frustrating. We cannot see a surface. We do not even know if a solid surface exists, or if pressures simply rise through exotic ices and supercritical fluids. We are inferring entire oceans and climates from a few wiggly lines on a graph, taken from a planet that orbits a star 124 light-years away. So it's time to find out the truth about what is at stake. If we can decode this one world properly, we are not just ticking a box that says, maybe habitable. We are redefining what that word means. That would reshape where we point our telescopes, what kinds of planets future missions are built to study, and even what sort of civilizations we imagine might share the galaxy with us. But to do that, we have to ask a harder question. What is K218b actually like from the inside out? And how close, or how alien, is its version of an ocean world? From big question to one weird planet, enter K218b. To answer that, we have to meet the planet itself. So let's begin with a name that, surprisingly, might become as famous as Mars or Europa, K218b. This is not a small, rocky, Earth-like world. It is a sub-Neptune exoplanet, about 2.6 to 2.7 times Earth's radius, and roughly 8 to 9 times Earth's mass. It orbits a cool red dwarf star in the constellation Leo, around 124 light-years away. On a galactic scale, that is practically in our cosmic neighborhood. What makes this planet stand out in the hunt for alien life? It sits in its star's Goldilocks zone, the habitable band where temperatures could allow liquid water to exist. But while thousands of exoplanets have been cataloged, only a small fraction occupy this delicate region. This means K218b immediately jumps out of the crowd. We are not just looking at any random world. We are looking at one where the basic thermal conditions for oceans might actually be met. It should be noted that location is only the first filter. The real reason K218b has become a superstar target is that we can study it in unusual detail. From our perspective on Earth, the planet passes directly in front of its star every orbit. Each transit lets starlight filter through its atmosphere, imprinting faint chemical fingerprints on the light that reaches our telescopes. Because K218b is larger than Earth and likely wrapped in a puffy, extended atmosphere, those fingerprints are stronger and easier to detect. Optimistically speaking, it is almost as if nature made this system specifically to be analyzed. But what kind of world are we actually analyzing? Here is where things get strange. K218b is too big and too light, on average, to be a simple rocky planet. At the same time, it is far smaller than the ice giants in our own solar system. So scientists have proposed a new category that might fit it perfectly, a Hycean world. Hycean, as the name suggests, is a hybrid. Imagine a deep global ocean, potentially hundreds of kilometers thick, buried beneath a substantial, hydrogen-rich atmosphere. Not a thin blue sky like Earth's, but a vast, light, insulating envelope that traps heat and shapes exotic weather. Above, a dim red sun. Below, a dark, pressurized sea. If K218b really is such a Hycean planet, then for the first time, we can do more than ask whether life is possible. We can start to ask what living there might actually feel like. From the upper atmosphere, down through the clouds, and into that abyssal global ocean. So it's time to find out the truth about what that would mean. JWST, the cosmic lie detector, turned on. K2-18b, and when you want to know what an alien ocean world is really like, you do not just guess. You point the most powerful space observatory ever built straight at it. So, let's begin with the James Webb Space Telescope. JWST is our flagship eye on the infrared universe, parked 1.5 million kilometers from Earth. Its golden mirror unfolded like a giant sunflower in the dark. It should be noted that infrared light is exactly where a cool, red dwarf star like K218's and a warm, cloud-wrapped planet like K218b shine brightest. This means Webb is almost custom-built for this specific system. But how do you read the atmosphere of a planet you can't even see as a separate dot? The trick is timing. Every few weeks, K218b passes directly in front of its star from our point of view. During that transit, a tiny fraction of starlight filters through the planet's atmosphere before it reaches JWST. Most of the light goes straight past, but a thin, glowing ring passes through whatever gases are there. Webb then splits that light into a spectrum, a rainbow stretched into hundreds of colors. Different molecules in the atmosphere, water vapor, methane, carbon dioxide, absorb very specific wavelengths. They carve out little bites in the rainbow. By measuring those missing pieces with extreme precision, JWST can tell us which molecules are present, and even, roughly, how much of each is there. In the hunt for alien life, that spectrum is our first interrogation. And JWST is an unforgiving cosmic lie detector. Its 6.5-meter mirror collects far more light than Hubble ever could, and its instruments are so sensitive they can detect a change in brightness of just a few dozen parts per million. Think about that. A minuscule dip in starlight crossing 124 light-years, then being dissected into chemical fingerprints. But while that sounds almost impossible, the data are real. For years, Hubble and other telescopes had hinted that K218b might have water vapor and a thick, hydrogen-rich atmosphere. Interesting, yes, but frustratingly vague. Was this a mini-Neptune with no solid surface, or a truly habitable Hycean world with an ocean in the Goldilocks zone? So it's time to find out the truth. When JWST finally observed K218b, the verdict was dramatic. It did not just confirm water vapor, it revealed a richer cocktail of gases, water, methane, carbon dioxide, far more consistent with a warm, hydrogen-wrapped world than a cold, icy giant. Optimistically speaking, it pushed K218b out of the generic sub-Neptune category and into something stranger. Pattern interrupt. One possible molecule in the data is, on Earth, strongly linked to marine life. What could that mean for the reality beneath K218b's clouds? Is this a steamy mini-Neptune, or an ocean world with life? So what is K218b really? Are we seeing a steamy, bloated mini-Neptune, or an ocean world where life might quietly thrive beneath a hydrogen sky? In the hunt for alien life, that is the central tension. The first possibility is the conservative one. K2-18b could be just a typical mini-Neptune, a planet about 2.6 times Earth's radius and several times its mass, wrapped in a thick envelope of hydrogen and helium. In this picture, there is no solid, walkable surface, only gas giving way to crushing pressures and scorching temperatures as you descend. Any water would be trapped deep below in exotic, high-pressure forms that make Earth's oceans look tame. It should be noted that worlds like this are probably common across the Milky Way. They are fascinating for planetary science, but for habitability, they are a problem. A deep, puffy atmosphere dominated by light gases tends to erase the gentle, stable conditions that life as we know it prefers. Chemistry is happening, yes, but it is happening in a regime more like the middle layers of Neptune than the blue surface of our own planet. If K218b fits this mold, then it is beautiful, alien, and almost certainly uninhabitable. But there is a second, far more provocative option. What if K218b is a Hycean world? In this scenario, the hydrogen atmosphere is relatively thin compared to a true mini-Neptune, sitting on top of a deep global ocean. Temperatures and pressures at a certain layer could cross into a sweet spot where liquid water is stable, where sunlight from its red dwarf star filters down as a dim reddish glow, and where chemistry can simmer for billions of years. This means that, although the planet is larger and puffier than Earth, it could host an ocean environment that is surprisingly gentle. JWST's data push us right onto this knife edge. We see water vapor, methane, and carbon dioxide in the atmosphere. That mix is perfectly consistent with a hydrogen-rich sky above a vast ocean, where water evaporates, methane and CO2 circulate, and perhaps even biological processes tweak the balance. But while that is one reading, there is a colder interpretation. The same gases can also be produced by non-biological chemistry in a more Neptune-like world, with no surface ocean at all. So it's time to find out the truth. Are we looking at a puffy, gas-dominated planet, impressive but sterile? Or a warm, ocean-covered world where chemistry has had an entire cosmic epoch to experiment with life? By the end of this video, after we explore the star, the planet's interior structure, its atmosphere, its climate, and even some speculative ecosystems, you will have a grounded sense of which side seems more likely. Optimistically speaking, we may even glimpse what life there would actually feel like. But to decide between these two futures for K218b, we first need to understand the strange star that is shaping its fate. Who's talking to you, and where we're going on this journey? So who is actually taking you on this trip to a distant red dwarf system? We should answer that before we dive beneath K218b's clouds. I'm the voice behind this channel, where we unpack real exoplanet data and then carefully push it to its imaginative limits. In the hunt for alien life, we try to balance wonder with discipline. Every dramatic possibility has to be chained to physics, chemistry, and what telescopes like JWST actually see. This means that when we talk about a strange, potentially ocean-covered planet, we are not just daydreaming. We are following the evidence as far as it will go. So let's begin by laying out the path for this journey. First, we are going to step back and really meet K218's star. What does it mean that it is a relatively cool red dwarf in Leo, 124 light-years away? How stable is its light? How intense is its radiation? And what does that do to any atmosphere in its Goldilocks zone? Before we talk about life, we need to understand the lamp that is trying to keep this world warm. Then we zoom in on the planet itself. K218b is not an Earth-like twin. It is a sub-Neptune, about 2.6 times Earth's radius, and several times more massive. We will break down what that size and gravity probably imply for its interior. Is there a rocky core, a deep global ocean, and then a puffy hydrogen envelope on top? Or something more exotic? That interior structure quietly controls everything that happens at the surface, if a surface even exists. Next comes the heart of the episode, JWST's atmospheric data. We will look at why water vapor, methane, and carbon dioxide show up in its spectrum, and what each of those gases might be telling us. It should be noted that even the tentative hint of dimethyl sulfide, if it holds up, would be extraordinary. But we will also ask the uncomfortable question, could non-biological processes mimic that signal? After that, we will stitch those clues together into a living picture: climate, clouds, sky color, and the behavior of a possible global ocean under a dim, red sun. What would weather feel like in a hydrogen-rich atmosphere? Could there be endless twilight storms, or calm, hazy days over deep, dark water? Only then do we let ourselves ask, what about life? We will build from simple microbial ecosystems in the high atmosphere to more complex ocean ecologies, to speculative civilizations adapted to a heavy, steamy world, and finally to human visitors trying to survive under alien skies. So it's time to find out the truth about K2-18b, not as definitely inhabited, but as a carefully constrained stage for possible biology. By the end, we will have walked from the light of its star, through its atmosphere, down into the darkest depths of its potential ocean, and back to the question, if life can exist here, what would it actually be like to meet it? Before the planet, why the star decides almost everything. If we want to imagine those alien oceans honestly, we have to ask a deceptively simple question first. What kind of light is shining on them? Because in the hunt for alien life, everything starts with the star. When astronomers talk about whether a planet is habitable, they are not just thinking about beaches and clouds. They are thinking about an energy budget. How much power is the star delivering per square meter? How stable is that delivery over billions of years? How harsh is the radiation that comes with it? This means that before we talk about any atmosphere, any ocean, or any possible biology on K2-18b, we need to understand the furnace that is driving the whole system. So let's begin by separating the problem into two layers. First, there is the star's side of the equation. Its brightness, its temperature, how often it flares, and how long it will live. Second, there is the planet's response. Its orbit, its atmospheric thickness and composition, its climate and chemistry. The star throws the pitch. The planet tries to catch it without dropping or burning it. K2-18 itself is a red dwarf, cooler and smaller than our Sun, sitting about 124 light-years away in the constellation Leo. But while it emits less total energy, K2-18b orbits much closer in, looping around its star in just about 33 days. The result is that this sub-Neptune receives a level of starlight comparable to what Earth gets from the Sun. In climate language, we talk about an equilibrium temperature, the balance point where incoming energy from the star matches outgoing heat from the planet. That balance places K2-18b squarely in the star's Goldilocks zone, where, with the right atmosphere, liquid water could exist. It should be noted that this equilibrium temperature is only a starting guess. Add a thick, hydrogen-rich atmosphere and strong greenhouse warming, and the real surface or ocean temperatures can shift dramatically. Strip the atmosphere away, and the planet freezes. But while the planet can adjust the details, the star sets the overall range it has to work with. There is another challenge here. We are trying to infer weather patterns, cloud decks, and maybe even biospheres from a few numbers about a distant star and some spectral lines from a transiting planet. That is an incredibly abstract exercise. Without a clear conceptual map, it is very easy to overinterpret the data and turn every interesting wiggle in a graph into a sign of life. So it's time to find out the truth about K2-18 by starting where the physics demands, with the central red dwarf, whose quirks echo through everything else. Its color will tint the sky, its variability will shape the rhythm of any day-night cycle, and its radiation will sculpt the chemistry of the atmosphere and ocean. Once we understand that stellar environment, then we can descend one level deeper and ask what K2-18b itself does with the light and heat it receives. Meet K2-18, a small, cool sun with a big personality. So if K2-18b is the stage, what kind of star is holding the spotlight? Because to understand any planet's chances for life, we first need to meet its sun. K2-18 itself is not a yellow, blazing sphere like our sun. It is an M dwarf, a red dwarf star, smaller, cooler, and far dimmer, with most of its light pouring out in the infrared. To our eyes, it would glow with a deep orange-red hue, more like a smoldering ember than a roaring furnace. This means that from K218b, the entire color palette of the sky, the ocean, and even potential biology could be shifted toward reds and near-infrared tones. Physically, K218 is modest. It has only about half the mass of the Sun and roughly half the Sun's radius. Its surface temperature is around 3,500 degrees Celsius, compared to the Sun's approximately 5,500, and its luminosity is only a few percent of our star's output. In the hunt for alien life, that faintness is crucial. K218 simply does not flood its system with energy the way our Sun does, so any habitable world must huddle much closer in to stay warm. Red dwarfs, like K218, are not rare curiosities. They are the rule of the Milky Way. It should be noted that they vastly outnumber Sun-like stars. Most of the nearest stars to Earth are red dwarfs. This means that if planets around these cool, dim stars can host stable atmospheres and liquid water, then the universe may be packed with habitable real estate, even if almost none of it looks truly Earth-like. But while red dwarfs offer quantity, they also bring serious problems. Many of them unleash powerful stellar flares and high-energy radiation, especially when young. Planets in the Goldilocks zone of such a star must orbit very close in to receive enough warmth, often just a few percent of the Earth-Sun distance. That proximity can strip atmospheres, alter chemistry, and lock a planet's rotation so that one hemisphere always faces the star. What does a world look like when one side bakes under a permanent red sun, while the other lies in eternal night? Around a red dwarf, the habitable zone is a tight ring, tucked right up against the star. So let's begin to picture K218b's situation. It completes an orbit in about 33 days, whipping around its star inside this close-in Goldilocks zone, bathing in infrared-rich light. Under such a spectrum, Rayleigh scattering is weaker, so the sky might not be Earth's bright blue at all, but a softer, darker, possibly even copper-tinted dome. So it's time to find out the truth. Under that dim, red sun, what does K218b actually do with this strange light, this close orbit, and this precarious gift of potential habitability? Red dwarfs versus life. Why these stars are usually bad news. To answer that, we have to confront an uncomfortable reality. In the hunt for alien life, red dwarfs like K218's star are usually the villains of the story, not the heroes. Why is that? On paper, red dwarfs look perfect. They are small, stingy with energy, and live for trillions of years. That should give any planet in the Goldilocks zone an almost absurd amount of time for life to appear and evolve. But while that sounds ideal, the detailed physics of these stars often turns their systems into cosmic minefields. The first problem is flares. Many red dwarfs, especially when they are young, unleash enormous stellar tantrums. These are not gentle solar storms. They are blasts of X-rays and extreme ultraviolet radiation that can be hundreds to thousands of times stronger than what Earth receives from the Sun. For a planet forced to orbit close in just to stay warm, that radiation can slam directly into the atmosphere, superheating it, driving powerful escape winds, and in the worst cases, stripping it away entirely. Imagine an Earth-like world that spends 1 billion years being sandblasted by flares. Oceans can evaporate, upper layers of the atmosphere can be peeled off, and any surface life is repeatedly sterilized. This means that even if a planet starts out with water and air, it may not keep them for long enough to become truly habitable. Then there is tidal locking. Because the Goldilocks zone of a cool red dwarf is so close to the star, the gravitational pull quickly forces planets into a locked state. with one hemisphere in permanent day and the other in endless night. At first glance, that sounds catastrophic. A blistering hot dayside, a frozen nightside, and a narrow twilight ring in between. Can an atmosphere really move heat around fast enough to prevent the air from freezing out on the dark side? It should be noted that strong winds and thick atmospheres could, in theory, smooth out these extremes. But if flares and radiation have already eroded that atmosphere, the planet is trapped in a vicious cycle. Less air means poorer heat redistribution, which in turn makes the climate even more unstable. Pattern interrupt. Even the color of the light works against familiar life. Red dwarfs emit most of their energy in infrared, with relatively little visible light. Photosynthesis, as we know it on Earth, is tuned to our sun's spectrum. Under a deep red sky, alien organisms might have to evolve entirely different pigments and energy pathways. The weaker blue light also changes how clouds reflect energy and how ice and water absorb it, reshaping climate feedbacks in ways that are still difficult to model. Optimistically speaking, some planets might thread this needle, but taken together, flares, tidal locking, atmospheric erosion, and unfamiliar light, most red dwarf systems look like harsh, unstable neighborhoods for Earth-like life. So let's begin to ask a sharper question. If red dwarfs are usually bad news, what makes the K2-18 system interesting enough that we have not written it off? So what makes K2-18's star a possible exception? If red dwarfs are usually villains in the story of habitability, could K2-18's star be a rare supporting character instead? This means we need to look very closely at how this particular star behaves, not just at the planet wrapped around it. Evaluating a red dwarf for life is often about one brutal question: how angry is the star? Many M-dwarfs unleash flares that are tens or even hundreds of times more energetic than anything the sun regularly throws at Earth. Proxima Centauri, for example, can spike its brightness in ultraviolet and X-rays by factors of 10 to 100 in minutes. A planet in the Goldilocks zone of a star like that is under near constant attack. K2-18, though, appears different. It should be noted that long-term monitoring with instruments like Kepler and ground-based telescopes shows variability, but not the relentless storm of superflares we see from the most notorious flare stars. Its flares seem less frequent and less energetic, more like modest solar storms than apocalyptic blasts. Some analyses suggest its high energy output is at least several times lower than that of extreme red dwarfs at similar ages. In the hunt for alien life, that relative calm is a big deal. But while a quieter star helps, it is only half the story. The other half is K2-18b itself. This planet is no fragile Earth twin, with a mass roughly 8 to 9 times that of Earth and a radius about 2.6 times larger. Its gravity is far stronger. That extra pull makes it much harder for a stellar wind to strip away gases. What would be a death sentence for a small rocky world, steady erosion over billions of years, can become manageable for a heavier mini-Neptune. And then there is the atmosphere. JWST data suggests K2-18b is wrapped in a hydrogen-rich envelope, possibly above a global ocean. Hydrogen is light, but in bulk it is an extraordinary blanket. A thick H/He atmosphere can transport heat efficiently from the permanent day side to the night side, smoothing out temperature extremes that tidal locking would otherwise exaggerate. So while one hemisphere always faces the star, the climate may not be split into blazing inferno and frozen darkness. This means that instead of a bare rock alternately scorched and frozen, we could be looking at a world with relatively gentle gradients, clouds, winds, and perhaps a broad band of temperate conditions. Optimistically speaking, K2-18's star is no gentle sun twin, but it is not a cosmic flamethrower either, and the planet is unusually well defended. So it's time to find out the truth. If the environment is this stable, What might the actual conditions on and within K218b be like? How we first met. K218b, a flicker in the constellation Leo. To understand those conditions, we have to rewind to the moment this world first revealed itself to us. Before K218b was a potential ocean planet with a protective atmosphere, it was just a flicker in the constellation Leo. Back in 2015, NASA's K2 mission, the extended life of the Kepler Space Telescope, was staring at thousands of distant stars, measuring their brightness over and over again. One of those was a faint red dwarf, about 124 light-years away. On one plot of brightness versus time, astronomers noticed something subtle, a tiny, regular dip in the light from this star. Then it happened again, and again. What could cause such a precise, repeating dimming? In the hunt for alien life, this is one of the most powerful clues we have. When a planet passes directly in front of its star, from our point of view, it blocks a small fraction of the starlight. This is the transit method. The star itself does not change, but its light briefly drops like a cosmic heartbeat every time the planet completes an orbit. By measuring how deep that dip is, astronomers can estimate the size of the planet compared to the star. A larger planet blocks more light. By measuring how often the dips recur, they can work out the orbital period, the length of a year on that world. For K218b, the signal said, a planet roughly 2.6 to 2.7 times Earth's radius, circling every 33 days, right in the star's Goldilocks zone. But while radius and orbit told us this was an intriguing world, they did not tell us what it was made of. Was this a scaled-up rocky super-Earth, or a puffier mini-Neptune wrapped in gas? To answer that, we needed mass. Follow-up observations from ground-based telescopes used the radial velocity method, watching the star wobble slightly as the planet's gravity tugged on it. This means we could weigh the planet indirectly. When the mass estimate came in, around 8 to 9 times Earth's mass, it should be noted that the combination of mass and radius pointed clearly to a sub-Neptune, too light and too large to be a purely rocky, Earth-like world, yet not as enormous as Neptune itself. Already, K218b was refusing to fit our simple categories. Then came Hubble. Astronomers used the Space Telescope to take low-resolution spectra during transits, essentially spreading the starlight into colors to see how the planet's atmosphere absorbed it. They saw hints of water vapor in a hydrogen-rich atmosphere, but the data were noisy, and multiple internal structures could still fit the observations: a deep ocean under gas, or a thick envelope over high-pressure ice. Optimistically speaking, we had a mysterious transit signal, a measured mass and radius, and a tantalizing but blurry atmospheric hint. So let's begin the next chapter. What happens when JWST turns its far sharper eye on this world, and the spectrum suddenly looks much less ambiguous? From numbers to a world. What we knew before JWST. Before JWST stepped in, K218b was a world mostly made of numbers, a radius about 2.7 times that of Earth, a mass around 8 to 9 Earths, an orbit of roughly 33 days around a cool red dwarf in Leo, placing it squarely in the Goldilocks zone. On paper, it sounded promising, but what did those numbers actually mean for a real physical planet? In the hunt for alien life, we often start with this basic checklist: size, mass, distance from the star. From that, astronomers estimated that K218b receives a similar amount of energy from its star as Earth does from the sun. This means its equilibrium temperature could, in principle, allow liquid water. Add one more clue. Early Hubble observations hinted at a hydrogen-rich atmosphere with signs of water vapor. It should be noted that for a sub-Neptune, that alone made it stand out. But while the measurements looked precise, the picture of the interior was anything but. This is the degeneracy problem. The same mass and radius can describe wildly different worlds. Was K2 K2-18b a mini-Neptune with a thick hydrogen and helium envelope over a compact rocky core? Or a deep global ocean planet wrapped in a lighter atmosphere? Or something in between with high-pressure ice layers and no true surface at all? To see why this mattered, consider two extremes. Imagine a planet with a huge gas layer where pressure and temperature climb so rapidly that any water becomes a supercritical fluid, neither classic liquid nor gas. Now imagine a slightly denser configuration where that gas layer is thinner and a vast liquid ocean can exist beneath it. Same mass, same radius, completely different prospects for a habitable environment. Hubble's atmospheric data only sharpened the mystery. Yes, there were signatures consistent with water vapor, but how much water? At what altitude? Was the atmosphere relatively clear, letting starlight pass through cleanly? Or was it dominated by clouds and hazes that hid deeper layers? The instruments simply lacked the resolution to tell. Even the temperature profile was uncertain, especially on the night side of this likely tidally locked planet. Here is the pattern interrupt. Before JWST, scientists could seriously propose both a potentially life-supporting ocean world and a suffocating, steam-shrouded mini-Neptune using the same basic data set. That is how wide the uncertainty was. Key questions piled up. Was there any solid surface, or just a gradual transition from gas to supercritical water and ice? Did a stable liquid water layer exist at any depth? Were pressures and temperatures anywhere in the planet compatible with known biochemistry? Or would complex molecules be ripped apart almost as fast as they formed? Optimistically speaking, K2-18b was less a vivid place and more a category label, a sub-Neptune in the habitable zone of a red dwarf. So it's time to find out the truth. How did JWST start turning that abstract category into a tangible world we can actually imagine standing on or floating within? So, habitable or not? Reframing the central question. So if K2-18b is finally starting to feel like a real place, we have to ask a much sharper question. Is this planet actually habitable in any meaningful sense? Or are we just projecting Earth's story onto a very alien world? On paper, the contrast is striking. K2-18b moves through the Goldilocks zone of a relatively calm red dwarf, bathing in just the right amount of starlight for liquid water. JWST has revealed a substantial atmosphere with clear signs of water vapor, methane, and carbon dioxide. In the hunt for alien life, that combination is almost irresistible. But while its orbit and chemistry sound promising, its size pulls us up short. This is not an Earth-like rock. It is about 2.6 times Earth's radius and around 8 or 9 times the mass, far closer to a mini-Neptune than to our own planet. So it's time to find out the truth. Can a world this big, wrapped in a hydrogen-rich envelope, really host stable, life-friendly conditions anywhere? If we rose up into its cloud tops, would we find a cool, temperate layer where droplets and hazes could shelter complex chemistry? Deeper down, could there be a global ocean, squeezed by gravity and pressure, yet still liquid and long-lived? Or does the immense weight of that atmosphere crush any potential habitat into an exotic, superheated abyss? It should be noted that habitable does not have to mean comfortable for humans. We tend to picture a rocky surface, blue skies, and continents, because that is what our own system has given us. But physics does not care about our preferences. From a scientific perspective, a habitable environment is any region where liquid water can persist, where energy flows, and where molecules have enough time to bump, react, and maybe assemble into something that can copy itself. That might be a shallow sea under a gentle sun, or a dim, high-pressure ocean buried beneath a hydrogen sky. Here is where the rhetorical doubt comes in. If we could somehow teleport Earth's entire biosphere to K2-18b, trees, fish, microbes, us, and spread it through the atmosphere and ocean, most of it would almost certainly die. The gravity would be stronger, the light redder and dimmer, the air dominated by hydrogen instead of nitrogen and oxygen. This means familiar metabolisms would be pushed far beyond their tested limits. But does that rule out life altogether? Not at all. Alien biology, born and tuned in those conditions over billions of years, might find them perfectly normal. Optimistically speaking, K218b forces us to stretch the very definition of a habitable planet. In the next segments, we will peel back the layers. First, we will confront the limits of our current data. Then we will build a system-level picture of this world, before finally zooming into specific regions, cloud decks, temperate strata, and possible deep oceans, where life, in principle, could make a living. How much can we really know from 124 light-years away? So if K2-18b might stretch the definition of a habitable planet, how much can we really trust what we think we know about it? From 124 light-years away, we are trying to reconstruct an entire world from the faintest possible clues. Everything we say about this planet rests on indirect measurements. We never see K2-18b directly. We watch its star dim by less than 1% as the planet crosses in front, and from those tiny dips in starlight, we infer its size, its orbit, even hints of its atmosphere. Then we pass that light through models of physics and chemistry and ask, which combination of gases could have created this pattern? This means that even JWST, powerful as it is not an all-seeing eye. Its spectra tell us that certain molecules, water vapor, methane, carbon dioxide, are present in the upper atmosphere, but they do not give us a weather map. We do not see where the clouds are thick or thin, how fast the winds blow, or exactly how deep any possible ocean might be. Is the water locked beneath high-pressure ice, or lapping against a relatively gentle hydrogen sky? Right now, the data simply cannot say. It should be noted that this is where model degeneracy enters the story again. Different mixtures of temperature, pressure, and composition can produce remarkably similar spectra. A slightly cooler atmosphere with more methane can mimic a warmer one with less. A deep global ocean under a thin hydrogen envelope might look, spectrally, a lot like a smaller ocean buried under a heavier atmosphere. In the hunt for alien life, that ambiguity matters. Two very different planets can hide behind nearly the same signal. And all of this is a snapshot in time. At this moment, with the JWST observations we have, K218b is a moving target. Future passes of the planet across its star, observed in different wavelengths, could sharpen the picture, or overturn parts of it. Next generation telescopes might separate out cloud layers, detect new molecules, or rule out others. Optimistically speaking, today's best fit model of a Hycean world could look crude, even naive, a few decades from now. So it's time to find out the truth, but carefully. In the next parts of this video, we are going to explore what life might be like on K218b based on the strongest, most consistent interpretations of the current data. When we lean on speculation, we will say so. We will not treat a single tentative biosignature claim as a final verdict on this world's habitability. Because the real question is not just what K218b might be today, but what hidden versions of this planet the universe is still keeping from us. Big picture habitability. Where could life hide on K218b? So if K218b might be many different hidden worlds at once, where exactly could life actually hide on it? In the hunt for alien life, this is the shift that matters. We stop asking whether the whole planet is friendly, and start asking whether any stable niche, any band or layer, quietly crosses the line into habitable enough. To do that, we need to picture K218b as a stacked world. At the very top, high in the hydrogen-rich atmosphere, there may be a region where pressures and temperatures look surprisingly Earth-like. Imagine a band of air where it is roughly room temperature. The gas is thin enough to be breathable with the right mix, and droplets of liquid water can form. This is not a solid surface. It is more like the altitude in Jupiter's atmosphere, where a human-built balloon could drift. But while Jupiter is deep frozen and blasted by radiation, K218b sits in its star's Goldilocks zone. So that same floating layer might be a genuine habitat. Deeper down, conditions likely become more exotic rather quickly. Here, models suggest a temperate zone where liquid water could coexist with dense hydrogen, forming a warm, compressed ocean of mixed fluids. It should be noted that this is not an ocean in the Earth-like sense, with clear blue water and crisp horizons. It might be murky, high pressure, and permanently dim. Yet chemistry does not care about aesthetics. If water is liquid, carbon-bearing molecules are present, and energy flows through, then this strange middle layer could host slow, resilient forms of life. Go deeper still, and we may hit a true global ocean, hundreds or even thousands of kilometers deep, resting on a mantle of high-pressure ice or rock. Here, pressures could be so extreme that ordinary biology, as we know it, would be challenged. But even on Earth, life clings to hydrothermal vents on the seafloor. Optimistically speaking, K218b might hide similar interfaces, where rock, ice, and supercompressed water meet. Why is any of this even plausible? Because K218b receives a similar total energy input to Earth, despite orbiting much closer to its red dwarf star. The star is cooler and dimmer, so the planet's tight orbit still places it roughly in the classic habitable zone. This means the top of the atmosphere, the mid-layer, and the deep ocean are all powered by a steady, long-lived furnace. Pattern interrupt. Notice what we have not talked about yet: its gravity, its exact internal structure, or how thick that atmosphere really is. Without those, we are sketching habitats on a blurred canvas, so it's time to find out the truth. In the next section, we will pin down K218b's bulk properties, its mass, radius, gravity, internal layering, and atmospheric depth. Only then can we start populating these niches with plausible alien ecosystems, and even ask where human technology might eventually float, swim, or anchor itself on this extraordinary world. A super-Earth or a mini-Neptune? The body of K2-18b. So if K218b isn't just a blurred sketch, what kind of body are we actually dealing with here? Is this a supersized Earth with oceans and continents? Or a shrunken cousin of Neptune with no real surface at all? So let's begin with the hard numbers. From transit and radial velocity data, we know that K218b's radius is about 2.6 to 2.7 times that of Earth, while its mass is roughly 8 to 9 Earth masses. This immediately places it in the sub-Neptune or mini-Neptune category. It should be noted that this is not what we usually mean by an Earth-like planet. This means we are dealing with something larger, puffier, and probably much more complex inside than a simple scaled-up rock. What does that do to gravity? If we divide mass by radius squared, we find that surface or near-surface gravity on K218b could be around 1.5 to 2 times Earth's, depending on how the interior is layered. Imagine weighing 150 to 200% of your current weight every moment of your life. In the hunt for alien life, that extra pull is crucial. It helps the planet hang on to a thick atmosphere, retain volatile gases like hydrogen and helium, and potentially support deep global oceans without boiling them off into space. But while the numbers are clear, the interior is not. One leading scenario is a dense, rocky, and icy core wrapped in a massive water layer, all topped by a hydrogen-rich atmosphere, perhaps hundreds or thousands of kilometers deep. In that picture, there could be a relatively sharp boundary where the gas ends and a global ocean begins, with pressure and temperature increasing rapidly as we descend. Another possibility is more Neptune-like. The outer envelope blends smoothly into supercritical fluids, substances that are neither ordinary gas nor liquid, with no solid surface where you could stand. Here, the planet's density becomes our main clue. Combine 8 to 9 Earth masses with a radius of 2.6 to 2.7 Earth radii, and the average density comes out far lower than a purely rocky world. It simply cannot be made of rock and metal alone. This means a substantial fraction of K218b must be volatiles: water, hydrogen, helium, and perhaps other ices. Optimistically speaking, it looks more like the exposed core region of an ice giant wrapped in a thick envelope than a blown-up terrestrial planet. Why does this layering matter for life? If there is a distinct interface where a liquid ocean meets a hydrogen-rich atmosphere, that boundary could be chemically rich, with energy gradients and mixing zones that resemble, in spirit, Earth's ocean surface and cloud decks. But if the transition from atmosphere to interior is smooth, merging into supercritical water and other exotic phases, it becomes harder to imagine familiar ecosystems. Harder, though not impossible. Floating microbial life could still inhabit temperate altitudes, riding convection cells in a deep alien sky. So it's time to find out the truth about that atmosphere-ocean boundary. In the next section, we will climb into K218b's hydrogen skies, map out pressures and temperatures, and ask where, in this towering envelope, liquid water and complex chemistry can actually coexist. Under a heavy sky, gravity, and what it feels like to stand there. So if K2-18b really has an ocean, what would it actually feel like to exist there, under that enormous hydrogen sky? To move, to breathe, to simply stand still in a world where gravity itself is turned up almost to double. From the mass and radius we have, the numbers tell a clear story. Gravity on K2-18b is probably around 1.5 to 2 times Earth's. This means your body weight effectively doubles. A 70-kilogram person would feel more like 110 or even 140 kilograms. Every step would hit harder. Your spine would compress more. Joints that feel fine on our planet might ache within minutes. In the hunt for alien life, we often focus on chemistry, but here, physics alone would challenge us. But while the pull downward increases, the sky itself changes too. Stronger gravity lets the planet's atmosphere cling more tightly to itself. It should be noted that a hydrogen-rich envelope under higher gravity can stack into very thick layers, with pressures building rapidly as you go down. Near any ocean interface, the air, or more accurately, the gas, could be incredibly dense and compressed, like standing at the bottom of a deep mine on Earth, multiplied many times. So let's begin imagining a more comfortable place. A floating habitat, parked at a level where pressure is similar to Earth's sea level. You step out into a controlled bubble, protected from the raw hydrogen outside. But the artificial gravity is set to match K2-18b's pull, so you can adapt. How would that feel? Lifting your arm takes effort. Climbing a ladder feels like hauling your body through waist-deep water. Even turning your head too quickly might leave your neck muscles protesting. Outside the walls, the dense hydrogen atmosphere would offer more resistance to motion than Earth's air. A probe falling through it would drop more decisively because of the higher gravity, yet feel a thick, almost syrupy drag as pressure rises below. Walking in an open, pressurized suit, if that were even possible, would be like hiking with a heavy pack while wading through a warm, invisible fluid. Gravity also sculpts weather. On a world like this, waves on any global ocean would be pulled down more strongly, becoming shorter and choppier rather than towering and slow. Clouds would sit in more compact, flattened layers because vertical motion is expensive in energy terms. Big storms might still form, driven by the red dwarf's heat and the planet's internal warmth, but their thunderheads would be squashed, their convection columns fighting against that relentless downward tug. Optimistically speaking, life adapted to this environment could be built low and strong. Squat floaters in the atmosphere, streamlined swimmers in the ocean, structures hugging pressure-favored layers. For us though, K218b would feel like living at the bottom of a very heavy sky. So it's time to find out the truth about that sky itself. What is this hydrogen envelope really made of, molecule by molecule? And where, inside it, could something truly Earth-like, and maybe even biological, actually survive? Breathing hydrogen, the strange atmosphere of K218b. If we could peel back that heavy sky, layer by layer, what would we actually see? Is K218b wrapped in something gentle and life-friendly? Or in a suffocating shroud that only alien chemistry could love? So let's begin with what the James Webb Space Telescope has already told us. Its spectra do not look like an Earth-like thin blue shell. Instead, they point to a hydrogen-dominated atmosphere with clear fingerprints of water vapor, methane, and carbon dioxide. This means we are dealing with a thick, extended envelope, more like a shrunken gas giant than a scaled-up Earth, swelling far above whatever passes for an ocean or surface below. Hydrogen changes everything. Compared to Earth's nitrogen-oxygen mix, hydrogen is much lighter, so the atmosphere puffs out and becomes far more expansive. Even with relatively modest amounts of heavier elements, it can trap heat very efficiently. In the hunt for alien life, that powerful greenhouse effect is crucial. It can keep deeper layers warm enough for liquid water, even though the planet orbits a relatively dim, red dwarf star in the Goldilocks zone. But while the overall picture is clear, the details by altitude are far stranger than anything on our own world. At the top, K218b likely has a high, tenuous exosphere, where hydrogen atoms are blasted by stellar radiation, and some may even escape into space. Drop down a bit, and we reach a middle region where temperatures and pressures might briefly pass through Earth-like values. Say, something comparable to a mountaintop, or the upper troposphere here. Pattern interrupt. That does not make it breathable. It should be noted that at no level could we simply step outside and inhale. Hydrogen itself is not breathable for humans. We need oxygen to extract energy. Methane and CO2, present at the levels JWST is measuring, would be toxic and disorienting. Even if the pressure felt familiar, a human without a full life support suit would quickly lose consciousness, then life, under this alien sky. Deeper still, the atmosphere compresses and heats until it may approach supercritical conditions, where the distinction between gas and liquid starts to blur. Here, water could exist as a hot, dense fluid, mingling with hydrogen and other molecules in ways that have no direct analog on Earth. Could exotic organisms float in these layers, using hydrogen and methane the way our biology uses oxygen and carbon-based nutrients? Optimistically speaking, physics does not forbid it. So it's time to find out the truth about the ingredients themselves. Now that we know the envelope is hydrogen-rich, what do the specific molecules, water vapor, methane, carbon dioxide, and that tantalizing hint of something more exotic, actually reveal about hidden oceans, chemistry, and the real prospects for life on this distant world? Water vapor, methane, and CO2. JWST's chemical portrait. So if K2-18b really has a hydrogen envelope, what is that envelope actually made of? In the hunt for alien life, this is where chemistry becomes our map. JWST did not just see a vague haze. It measured specific fingerprints of molecules written into the infrared light from the planet's atmosphere. So, let's begin with the most familiar one, water. When K2-18b passes in front of its red dwarf star, some starlight filters through the atmosphere. At certain infrared wavelengths, that light is absorbed more strongly. Those dips in the spectrum line up beautifully with known absorption features of water vapor. This means there is a significant amount of H2O high in the atmosphere, not just buried deep below the clouds. But what does that really tell us? Water vapor at those altitudes is consistent with moist air above a liquid water layer, or with water mixed into a deep, warm hydrogen envelope. If the temperatures were extremely high, water would be broken apart more efficiently. Instead, the pattern JWST sees fits an atmosphere that is warm but not furnace hot, entirely compatible with a potential global ocean somewhere below. Next come methane and carbon dioxide. JWST detected clear signatures of CH4 and CO2, revealing that K2-18b has a carbon-bearing atmosphere with active chemistry. Methane tends to prefer cooler, reducing environments, while carbon dioxide becomes more dominant at higher temperatures or with stronger oxidation. Their relative amounts can hint at the pressure and temperature structure, and even tell us whether the gases are in simple chemical equilibrium or being constantly disturbed. But while equilibrium chemistry would produce some mixture of these gases automatically, departures from that balance, so-called disequilibria, can point to strong photochemistry driven by the star's radiation, or to continuous outgassing from the planet's interior. On K2-18b, the combination of H2O, CH4, and CO2 fits remarkably well with the Hycean scenario, a hydrogen-rich atmosphere overlying a deep water layer with starlight and internal heat endlessly reshuffling the molecules. It should be noted that none of these molecules, by themselves, are evidence for life. Water vapor, methane, and carbon dioxide can all be produced by completely non-biological processes: volcanism, reactions between rock and water, and ultraviolet light breaking and rebuilding molecules in a hydrogen atmosphere. Optimistically speaking, they tell us the planet is chemically rich and potentially habitable, but not that it is inhabited. So it's time to find out the truth about that something more exotic. Buried in the same JWST data is a tentative hint of a fourth carbon-bearing molecule, dimethyl sulfide, or DMS. On Earth, almost all atmospheric DMS comes from marine life. Could K2-18b really host an ocean biosphere producing it? Or is this signal an illusion? That controversy is where the story becomes far more dramatic. The DMS whisper, a tentative hint of alien biology? So what is this mysterious dimethyl sulfide actually telling us? In the hunt for alien life, it might be one of the strangest clues we have ever seen. Because on our own planet, DMS is almost a love letter written by the oceans. Dimethyl sulfide is a sulfur-containing molecule. Here on Earth, nearly all of it in the atmosphere comes from tiny marine organisms, phytoplankton, and the bacteria that process their remains. These microscopic drifters make precursor compounds inside their cells. When those break down, DMS escapes into the air. Once there, it seeds clouds over the oceans, subtly cooling the climate. This means, if you look at Earth from space and detect a strong DMS signal, you are, indirectly, seeing the breath of a living ocean biosphere. So let's begin with what JWST actually saw at K2-18b. When the planet passes in front of its red dwarf star, starlight filters through its atmosphere. By spreading that light into a spectrum, we can see dark fingerprints where specific molecules absorb. In some early analyses of the JWST data, researchers noticed a faint dip at wavelengths where DMS is expected to absorb. It should be noted that this is not a bold, screaming feature. It is a subtle wiggle right at the edge of what the instruments can reliably distinguish from noise. Why did that tiny wiggle cause such excitement? Because on Earth-like worlds, we do not know of any strong, non-biological way to pump DMS into an atmosphere. Volcanoes, hydrothermal vents, and lightning do many things, but they are not major DMS factories here. So, optimistically speaking, if you saw a clear DMS signal on a temperate, ocean-covered, Earth-like planet, you might start whispering the word biosignature. But while that sounds thrilling, the situation for K218b is far more fragile. The possible DMS feature appears only in some models of the spectrum, and it changes depending on how you assume the temperature, clouds, and other gases are layered in the atmosphere. Shift those assumptions slightly, and the apparent signal fades or disappears. Add more data from future JWST transits, and that delicate bump might either sharpen into something real or melt back into statistical noise. So it's time to find out the truth, but we are absolutely not there yet. And even if DMS were confirmed beyond doubt, we would still face a deeper question. What does DMS mean on a Hycean world that is not truly Earth-like? K218b likely has a hydrogen-rich envelope, higher pressures, different chemistry, and far more intense ultraviolet light from its star. Exotic geochemical or photochemical pathways might exist that we simply have not modeled. Could reactions in a warm, high-pressure ocean or strange sulfur cycles in the upper atmosphere produce DMS without life at all? In the hunt for alien life, DMS on K218b would be a whisper, not a shout. It pushes us to imagine vast alien seas filled with plankton-like organisms exhaling sulfur into a hazy sky, but forces us to treat that image as a question mark, not proof. The real test will come when we ask, what other clues can we gather, and do they all point in the same direction? A red twilight world, light, color, and the alien sky. So if DMS is only a whisper, what would the rest of this world actually look like to our eyes? Imagine opening a visor and seeing daylight that feels more like standing inside a sunset. K218 is a cool red dwarf, pouring out most of its energy in the infrared. This means its light is rich in deep reds and invisible heat, but relatively poor in blues. On Earth, our bright yellow sun and blue sky shape almost everything about how we think a habitable planet should look. Here, the entire color palette shifts. The star would paint the sky in copper and rose, less like noon on Earth, and more like the last 15 minutes before the sun dips below the horizon. But while the star itself is red, the atmosphere of K218b would do a lot of creative editing. A thick, hydrogen-rich envelope, laced with haze and towering clouds, would scatter and absorb that light in unfamiliar ways. Shorter, bluer wavelengths would be stripped out first, leaving a muted, pastel dome overhead. Near the star, you might see intense bands of crimson and purple bleeding through gaps in the clouds, while the rest of the sky glows as a soft, diffuse wash, almost like light filtering through frosted glass. From a mid-atmosphere vantage point, perhaps on a floating platform or a high-altitude balloon habitat, the star itself would look strange. Because K218b orbits close in the Goldilocks zone of its system, the star would appear larger in the sky than our sun does from Earth. Yet it would still feel dimmer to human eyes, its visible light smeared into a gentle, smoldering ember rather than a blinding disk. If the clouds are thick, you might never see a sharp star at all, just a brighter patch in a permanent twilight ceiling. Here is the pattern interrupt. Close your eyes and ask, how would life even see in a place like this? In the hunt for alien life, we usually picture green leaves under blue skies. On K218b, alien phototrophs would face a very different challenge. They would want to capture as much red and infrared as possible, without overheating. This could drive pigments that look almost black to us, absorbing a huge slice of the spectrum, or bizarre, mirror-like surfaces that reflect away excess heat while sipping specific wavelengths for photosynthesis. It should be noted that this red-shifted world would shape not only biology, but technology. Human habitats might be lit by cool, artificial daylight inside, while outside, Instruments and cameras would be tuned to the infrared glow that actually carries most of the energy. So let's begin to fix this in our minds. K218b as a dim, copper-washed planet where day never becomes truly bright and sunset never fully ends. So it's time to find out the truth about what kind of ecosystems and perhaps civilizations could grow under that endless red twilight. Weather on a Hycean world, storms, winds, and alien clouds. If the light on K218b is forever sunset, what does its weather look like under that endless twilight sky? Because once we understand the storms and winds, we start to see where this planet could actually shelter life, and where it would be utterly hostile. A hydrogen-rich atmosphere does not behave like Earth's thin shell of nitrogen and oxygen. It should be noted that hydrogen is light, easy to stir, and an excellent carrier of heat. Wrapped around a sub-Neptune in close orbit around a red dwarf, it becomes a powerful greenhouse blanket. This means the day side of K218b could soak up energy from its dim star, while the night side remains permanently dark, yet both are tightly linked by ferocious circulation trying to even things out. If K218b is tidally locked, as models strongly suggest, one hemisphere always faces the star. On Earth, weather is driven by the daily spin and tilted seasons. Here, the big contrast is simpler but more extreme. A fixed, hot pole under the red sun, and a cold, eternal night beyond the Terminator. In the hunt for alien life, that sharp day-night divide may be just as important as distance in the Goldilocks zone. So what would we actually see if we could look down through that hydrogen sky? Where moist air rises under the substellar point, it would cool and condense into towering water clouds, likely merging into a thick, bright cloud deck. Imagine a vast, circular shield of cloud permanently glued to the day side, reflecting some starlight but trapping infrared heat below. At the edge of that shield, air would spill outward and over the Terminator, stretching into long, trailing cloud systems that spiral across the night side like ghostly streamers. Those contrasts drive winds, strong ones. With a deep, puffy atmosphere and a rapid flow from hot to cold, high-altitude jet streams could reach hundreds of kilometers per hour, racing around the planet in broad bands. But while the upper layers roar, deeper down, closer to any global ocean, the winds might slow, forming stacked layers with very different conditions from top to bottom. Inside those layers, storms would be spectacular. Deep convective towers could punch upward for hundreds of kilometers, powered by warm, moist air rising from the ocean. In their cores, water drops and ice grains, colliding in a hydrogen-rich environment, might generate lightning, flashing within murky clouds that never fully clear. We might even see long-lived vortices, colossal storm ovals, reminiscent of Jupiter's great red spot, but in a warmer, wetter, more Earth-like pressure regime. Optimistically speaking, such violence does not rule out habitability. It carves out niches, stable bands with moderate temperatures, lower shear, and persistent cloud cover could act as atmospheric oases above the worst turbulence. In those zones, floating or planktonic organisms could drift in the upper ocean or hover in the air, feeding on chemical gradients and filtered red light. So let's begin to think of K218b not as uniformly calm or hostile, but as a layered weather machine, where the next question is how any ecosystems might adapt to such an alien climate. The global ocean hypothesis, an endless sea with no shore. If the atmosphere is a layered weather machine, what lies beneath it? On K218b, many researchers think the answer is both simple and terrifying. Water. Not scattered in lakes or seas, but as a single, planet-wide ocean with no shore at all. This is the essence of the Hycean model. In this picture, K218b is not a rocky, Earth-like world with continents. Instead, beneath its hydrogen-rich atmosphere, a deep, global ocean wraps the entire planet. No coastlines, no islands, just an unbroken horizon in every direction, over a sphere more than twice Earth's size. It should be noted that this ocean could be hundreds of kilometers deep, far beyond anything we see on Earth, where the deepest trenches barely reach 11 kilometers. Near the top of that ocean, conditions might be deceptively gentle. Under the filtered glow of its red dwarf star, temperatures could sit in a range where liquid water is stable, perhaps not so different from the upper few hundred meters of our own oceans. Waves would roll beneath thick clouds, and the hydrogen atmosphere above would trap heat, smoothing out extremes between day and night. But while the surface layers might be relatively temperate, the descent below would be a one-way journey into extremity. With roughly 8 times Earth's mass, gravity and pressure on K218b climb rapidly. Every kilometer down adds crushing weight, tens, then hundreds of thousands of times Earth's surface pressure. This means water there would not behave as the familiar liquid we know. At depth, rising temperature and pressure could push it into supercritical water, neither true liquid nor gas, or lock it into exotic, high-pressure ices that are solid yet hotter than boiling water on Earth. Chemically, this global ocean would be just as alien. The hydrogen-rich atmosphere above and the planet's interior below would continuously feed it with gases like hydrogen, methane, and CO2. In the hunt for alien life, those dissolved gases are not just curiosities, they are potential energy sources. Gradients in salinity, pH, and nutrient content could form as interior outgassing injects minerals from below, while atmospheric exchange rains oxidants and organics from above. So let's begin to imagine the scene. At the surface, the sky is dim and red, the star a small ember behind thick, gray-black clouds. The ocean itself would be almost black, swallowing light within a few tens of meters. Deeper down, true night would fall, and if life exists, bioluminescent flashes, blues, greens, maybe eerie reds, might be the only illumination, like drifting constellations in a liquid sky. Optimistically speaking, such an ocean could host complex ecosystems, from floating mats near the light to chemotrophic communities feeding on interior heat. But with no land, no shallow coastal zones, and no tidal pools, do the usual pathways to complexity even exist here? Or is K218b's sea destined to remain a mostly microbial, diffuse biosphere, invisible even to JWST's incredible data? So it's time to find out the truth about what that would mean for actual living organisms, and for us. Life in the depths. Could an entire biosphere float? If K218b really has an ocean, what does it actually feel like to be a living cell in that endless alien sea? In the hunt for alien life, we often jump straight to creatures and civilizations, but any biosphere here would begin with something far smaller and far stranger than us. So let's begin at the scale of microbes, drifting in the upper, light-washed layers of a hydrogen-rich ocean. Under a dim red dwarf star, visible light is weaker, but infrared is strong. This means photosynthetic or phototrophic organisms might use pigments tuned to deep red and near infrared, harvesting energy from wavelengths that feel almost like gentle heat. Alongside them, chemotrophs could tap into dissolved hydrogen, methane, and other reduced compounds, using redox reactions the way Earth's bacteria exploit oxygen and sulfur. Together, they would form a floating film of metabolism, the true base of the food web. But how do you build an ecosystem when there is no seafloor you can safely reach and no land to anchor to? One answer is to never sink. We can imagine plankton-like organisms evolved to be perfectly buoyant, with gas-filled bladders or ultra-low-density tissues that keep them parked at just the right depth for light and nutrients. Some might slowly migrate up and down each K2-18b day, tracking the star's faint arc across the sky. It should be noted that if any of these microbes, or plankton analogs, produce dimethyl sulfide-like molecules as waste, those gases could leak upward into the atmosphere. And that is exactly the sort of signal JWST is now searching for. Then comes the next step, size. If microbial blooms form dense, drifting clouds, why not larger filter feeders to graze on them? Picture vast, translucent bodies, a little like jellyfish, but adapted to a warm, infrared-bathed ocean. Some might be dark, almost black, to absorb precious photons. Others could be mirror bright, reflecting excess energy to avoid overheating. With light scattered and absorbed in the upper layers, vision might be unreliable. Predators could instead sense pressure waves, like hypersensitive sonar, or even use electric fields, mapping the water column in three-dimensional detail without ever seeing, in our sense of the word. Pattern interrupt. What if the most vibrant ecosystems are not near the light at all, but far below, at the base of the ocean, where a rocky or icy mantle meets liquid water? Hydrothermal vents could roar with chemical energy. There, chemosynthetic communities might thrive, feeding on hydrogen, methane, and metal-rich fluids, much like Earth's deep-sea vent systems, but perhaps scaled up across an entire planet. Optimistically speaking, could intelligence arise in such a world? In a global ocean with no land, tool-using life might seem unlikely. Yet organisms could still exploit the ocean-atmosphere interface, weaving floating mats, bubble-supported rafts, or even rigid frameworks made from precipitated minerals and organic polymers. A truly advanced species might learn to trap hydrogen for lift, build permanent drifting cities, and use chemistry and sound as their versions of electricity and radio. So it's time to find out the truth. If such a floating civilization exists, could any of its activity ever be visible across 124 light-years? Or would we only ever see the faint atmospheric fingerprints of the microbes that started it all? Cities in the clouds, atmospheric life, and sky civilizations. But what if those drifting cities are not the exception on K218b, but the rule? In the hunt for alien life, we usually picture oceans and rocky coasts. Yet there is a third option that on a Hycean planet might be even more important. A biosphere that never touches liquid water or solid ground, living entirely in the atmosphere. So let's begin by imagining an endless, three-dimensional sky where surface is a meaningless word. On Earth, we already have tiny hints of this idea. Bacteria, spores, even insects can ride air currents for days. But while those are visitors, an atmospheric ecosystem on K218b could be permanent residents. Think of organisms adapted to a warm, hydrogen-rich atmosphere, floating in pressure layers that feel almost Earth-like, feeding on sunlight filtering from the red dwarf star above, and nutrients lofted from the hidden ocean below. What might such creatures look like? One obvious strategy is buoyancy. Balloon-like bodies could evolve, filled with gases lighter than the surrounding hydrogen, perhaps helium, or even metabolically warmed hydrogen itself. Some might be as small as seeds. Others could rival hot air balloons, translucent bladders with dark, photosynthetic tissues hanging beneath, turning the upper atmosphere into a drifting forest of living lanterns. But buoyant balloons are only the beginning. Other organisms might grow wing-like or fin-like sails, not for flapping flight, but to surf powerful updrafts and jet streams that circle the planet. Long, ribboned bodies could twist to climb or dive through different temperature layers, choosing the altitude that gives the best mix of light, chemistry, and safety. It should be noted that on a world with stronger gravity than Earth, riding the wind could be far more efficient than fighting it. Then there are the colonies. Picture vast, gauzy mats of interconnected organisms stretched across stable atmospheric layers, like floating coral reefs. They could trap droplets, host symbiotic microbes, and slowly drift around the planet's limb, casting thin shadows on the clouds below. This means the ground of a sky civilization might be a living, flexible platform. So how would intelligence change this picture? An advanced species evolving here might never see rock. Their cities could be enormous, engineered bladders and towers of composite fibers, anchored by massive reservoirs of buoyant gas. Transportation would follow the winds, skyships that ascend into fast jets to cross the planet, then sink into calmer layers to dock with floating habitats. Without easy access to metals locked deep below, technology would need a different foundation. Organics, ceramics, and perhaps ice-reinforced structures at cooler heights might replace steel. Energy could come from sunlight, from chemical gradients in the atmosphere, or even from heat engines exploiting vertical temperature differences, machines that literally feed on the planet's own weather. Optimistically speaking, such a civilization could become exquisitely tuned to its atmosphere, predicting storms days in advance, surfing safe corridors, and building radiation shelters in denser, shielded layers. But they would always face risk: sudden turbulence, flares from the red dwarf, long-term climate shifts. Home would never be still. And that raises a final question. If your species had evolved in the clouds of a Hycean world, with no memory of continents or mountains, how would you think about stability, ownership, even belonging? Would home be a specific place on the planet, or a moving band of pressure and temperature forever circling in the sky, setting the stage for how we might one day meet them? A day in the life, time, seasons, and daily rhythms on K2-18b. If home is a moving band in the clouds, what does a day even mean? On K2-18b, the answer is stranger than anything we experience on Earth, and it all starts with how this planet dances around its star. K2-18b completes an orbit in just about 33 Earth days, so a year there is barely more than a month for us. But while we measure our lives by the familiar 24-hour spin of Earth, this world is so close to its red dwarf that gravity likely grips it tightly. This means K2-18b may be tidally locked, always showing the same face to its star, just as the moon does to Earth. If that is true, there is no sunrise for half the planet. The day side would live under a permanent, dim, red noon, the star frozen in the same patch of sky. The night side would never see the star at all, only the glow of the atmosphere and the faint shimmer of starlight scattered from the bright hemisphere. Between them lies the terminator, a ring of eternal sunrise and sunset, where the red dwarf forever hovers on the horizon. In the hunt for alien life, that ring could be precious. A tidally locked Hycean world might channel fierce winds and currents around the terminator, smoothing out temperature extremes and creating a relatively stable twilight belt in the global ocean below. Life, if it exists, might cluster where light is gentle but not absent, and where the atmosphere constantly mixes heat and nutrients. But there is another possibility. K2-18b might not be perfectly locked, instead rotating in a slow resonance with its orbit. In that scenario, a single day could last many Earth days, with long, drawn-out mornings and evenings as the star crawls across the sky. It should be noted that even then, the planet's thick hydrogen atmosphere would blur the contrast between day and night, turning sharp shadows into a continuous, coppery glow. What about seasons? Around a small red dwarf, close-in planets tend to have small axial tilts because tidal forces gradually straighten them. So K2-18b may barely lean at all. That means minimal seasonal change. No shifting bands of climate marching north and south. No winter darkness or summer blaze. Year after 33-day year, conditions could be remarkably similar, almost monotonous on geological timescales. So how do biological clocks work in a place with no clear 24-hour cycle? Optimistically speaking, life there might lock onto subtler rhythms, tiny fluctuations in light as high-altitude clouds pass, regular pulses of atmospheric tides driven by the star's gravity, or slow temperature waves propagating around the planet. Sleep might not be at night, but during cooler phases of a pressure cycle. Predators could hunt when the winds shift, not when the sky darkens. Now imagine yourself in a floating habitat, suspended high in that hydrogen sky. Morning is when the red glow brightens by a few percent and distant cloud bands sharpen, not when the star rises. Evening is when the wind pattern changes and the ocean far below radiates a bit more heat. You might schedule work around the passage of a recurring jet stream, or celebrate the rare alignment when a brighter than usual flare bathes the atmosphere in extra light. So it's time to find out the truth. In a world where the clock is written in winds and tides instead of sunshine and shadows, how would technology, culture, and even memory adapt? And what surprising constraints might that place on any civilization that calls K218b home? Could we go there? Human physiology meets a Hycean world. So if the clocks of K218b are written in winds and tides, where do we fit into that story? Could a human body, built for one fragile blue world, actually survive on a Hycean planet that weighs several times more than Earth? Evaluating that means facing the raw physics first. K218b likely pulls at us with around 1.5 to 2 times Earth's gravity, under an atmosphere rich in hydrogen and methane, with pressures that climb brutally as you go down toward the deep global ocean. There is probably no solid land in the traditional sense, no continents for cities, no mountains to anchor launch pads. This means the romantic idea of simply standing on K218b is almost certainly impossible. So let's begin with immediate survival. Where could we actually exist? Our best option would be a narrow, relatively gentle layer in the atmosphere, where temperature and pressure are close to what we tolerate on Earth. There, we would need fully sealed, pressure-controlled habitats, floating platforms or dirigible-like stations, holding Earth-like air, recycling water, and keeping temperatures stable as the red dwarf brightens and dims. It should be noted that even in this safer band, radiation from the star and charged particles trapped in the planet's magnetic environment could be intense, demanding robust shielding. But while a habitable pressure is essential, gravity is the slow, relentless enemy. At 1.5 to 2 G, every step would feel like walking with a person on your back. Our hearts would struggle to pump blood upward, our leg muscles and spines would live under constant overload, and even simple movements could raise the risk of injury. How do we fight that? We might rely on powered exoskeletons to amplify motion, compression suits to help circulation, and carefully designed rotating habitats inside our floating stations, where spinning rings simulate more Earth-like gravity for rest and long-term health. Here is the pattern interrupt. Maybe we would barely walk on K2-18b at all. Instead, human life might unfold mostly inside these rotating micro-city habitats, with forays into the higher gravity exterior kept short, like deep-sea dives on Earth. Over generations, the planet itself could begin to shape us. In the hunt for alien life, we often imagine microbes adapting to their star and atmosphere. But what about us adapting to this world? Optimistically speaking, either natural selection or deliberate genetic engineering could favor shorter, more compact bodies, denser bones, and reconfigured circulatory systems with stronger hearts and higher blood pressures, all tuned to 1.5 to 2 G. Our descendants might look less like tall Earth athletes and more like sturdy, low center of gravity specialists built for weight. So it's time to find out the truth about feasibility. Raw K2-18b is utterly hostile to unprotected humans. Yet with advanced engineering, careful habitat design, and a willingness to let the planet change us as much as we change it, we could carve out thin, floating niches in its atmosphere if the scientific payoff and the chance to share a system with possible alien oceans below is worth the cost. And if we did all that, what would we actually see and study from those drifting cities in the hydrogen sky? Engineering floating habitats, how we'd build homes in the sky. So if we had those drifting outposts already in place, could we turn them into full-scale cities in the sky? To answer that, we have to imagine not just visiting K2-18b's atmosphere, but learning to live inside it. In the hunt for alien life, we usually picture solid ground and oceans below our feet. But here, the safest surface might be a stable layer of hydrogen air at pressures and temperatures surprisingly close to Earth-like. This means we can borrow a concept first proposed for Venus: vast aerostat cities, balloon-supported structures that float at a fixed altitude, riding a Goldilocks zone not around a star, but inside a planet's atmosphere. Only this time, everything is immersed in a light, hydrogen-rich envelope under higher gravity. So let's begin with buoyancy. On Earth, hot air balloons rise because warm air is less dense than cold air. In a hydrogen sky, hydrogen itself is the background gas, so we need to be more creative. One strategy is to heat hydrogen inside giant envelopes, using waste heat from reactors or sunlight to make it expand and lighten. Another is to fill lift cells with helium, which is heavier than hydrogen as atoms, but forms a slightly less dense gas at the same temperature and pressure. It should be noted that in such a dense atmosphere, even small density differences can generate enormous lift, especially when gravity is stronger than Earth's. Engineers might even experiment with vacuum cells, rigid, ultra-strong shells that enclose nothing. In a thick atmosphere, the pressure difference could provide powerful buoyancy if materials can survive the crushing forces. Higher gravity pushes designs toward compact, high-strength structures, but the rich atmospheric density helps by allowing smaller volumes to support larger masses. What would these habitats actually look like? Picture multi-level platforms suspended beneath vast, layered balloons. The upper decks would be wrapped in shielding against cosmic radiation and energetic particles from the red dwarf star, forming a protective roof. Below that, pressurized living modules, labs, and greenhouses would open onto panoramic galleries, with observation decks looking down into the deeper, darker hydrogen layers. Tethered drones could dive below, sampling clouds and chemistry. More robust submersibles might ride cable elevators all the way to the suspected global ocean, dipping in briefly to collect water, organics, and perhaps biological material, before climbing back to the safer, temperate band. Power is the next challenge. Under a dim red dwarf, solar panels must be broad, dark wings, tuned to red and infrared light. But while the star is faint, the winds may be fierce. Turbine farms hanging above and below the cities could tap jet streams that circle the planet endlessly. Between warm upper layers and cooler depths, we could run thermal machines that exploit vertical temperature gradients, generating electricity day and night. Optimistically speaking, these floating habitats would evolve from lifeboats into laboratories. So it's time to find out the truth. Could they become permanent research stations and listening posts, quietly watching the atmosphere for changing biosignatures and the ocean below for hints of chemistry that looks suspiciously like life? If K2-18b does host a hidden biosphere, our sky cities might be the first human-made objects to share a world, however carefully, with truly alien ecosystems. And if we were patient enough to watch those systems change over decades, what kind of weather, seasons, and maybe even biological rhythms would we witness unfolding beneath that dim, crimson sun? Seeing the unseen, how we'd explore oceans and skies remotely. If we can't live in those sky cities yet, how do we touch a world like this without ever setting foot there? In the hunt for alien life, K218b forces us to think like patient puppeteers, pulling strings from light years away. So let's begin with the atmosphere. Before we ever dream of oceans, we drop robotic scouts into that hydrogen-rich sky. Picture an entry capsule slamming into the upper layers, wrapped in a heat shield, then peeling open to release a fleet of explorers. Helium balloons that float at Goldilocks altitudes, gliders that surf vertical winds, and powered drones that can climb and dive through the haze. Each one would sniff the air for water vapor, methane, CO2, and more exotic molecules, while mapping temperature, pressure, and wind speeds from the high, cold layers down toward the warm, potentially habitable zones. But while balloons give us long-lived, drifting observatories, they are blind to what lies beneath the clouds. To reach the ocean, we need a second act. Imagine a floating platform that splashes down on the dark, endless sea, then quietly releases autonomous submersibles. These robot fish would be built to endure crushing pressures, with thick hulls and careful thermal control, creeping through the water column and sending pings of acoustic data back to the surface. Some might stay tethered by fiber optic cables to the float. Others could roam freely, returning periodically to upload their memories to an atmospheric relay balloon. What would those memories contain? This means prioritizing very specific kinds of data. We'd want detailed chemical profiles of the air and water, down to parts per billion, and isotopic ratios of elements like carbon, nitrogen, and sulfur that can betray biological processing. We'd measure the size, shape, and composition of aerosols and cloud particles, asking whether they are simple hazes or something more like organic smog. In the ocean, cameras and microscopes would search for particulate matter, from mineral grains to plankton-like flecks, watching how they move, clump, and maybe even respond to light from the distant red dwarf star. It should be noted that none of this is easy to talk to. Signals from a deep sub must first fight their way to the surface, then to a balloon or drone, then to an orbiter high above the planet, and only then across 124 light years to Earth. Every message takes over a century round trip, and bandwidth would be painfully limited, forcing us to choose between a handful of images, spectra, and sensor logs. Optimistically speaking, we could still reconstruct a living picture, but never in real time. So it's time to find out the truth about where we actually stand. For now, JWST itself is our only probe, reading K218b's atmosphere by dissecting its spectrum as the planet crosses its star. Yet by imagining these future missions in detail, we sharpen the questions we ask Webb today. Which molecules matter most? Which spectral fingerprints hint at oceans? Which strange combinations might whisper life? And if one of those fingerprints really does whisper, what kind of message would we dare to send back across that hydrogen sky? Alien eyes and alien minds. How life here might perceive reality. If something on K2-18b did answer us, how would it even sense that we were there? We imagine telescopes, radio dishes, familiar eyes staring back. But on this planet, under a dim red dwarf and a hydrogen-rich sky, reality itself would be filtered through very different senses. So, let's begin with vision. Under K218b's red-dominated light, colors like we know them almost disappear. The star pours out more infrared than bright white. This means any eyes here, if eyes exist at all, might be tuned to heat, not hue. Imagine a creature in the upper ocean that sees the world as shifting gradients of warmth. A warm plume rising from a vent, a cooler shadow where something dense blocks the light, a faint infrared glimmer from bioluminescent fluorescent partners below. Instead of blue seas and green plants, their spectrum might be a tapestry of temperature and brightness. But while we lean heavily on color, life here could exploit something else entirely: polarization. Light scattering through a thick hydrogen atmosphere and reflecting off endless waves would be strongly polarized. An intelligent swimmer might see crisp polarization patterns where we would see only murky twilight, reading currents, clouds, even the angle to the star from subtle shifts in the sky. Non-visual senses would likely dominate. In a deep global ocean, pressure is information. Picture long, sensitive organs running along a creature's body, feeling tiny changes in pressure as waves, currents, and distant motions roll past. One flick of a fin a kilometer away becomes a clear signal. Chemoreceptors could be just as refined, tuned not only to oxygen or carbon dioxide, but to delicate gradients of methane, carbon dioxide, and maybe even dimethyl sulfide drifting through water and atmosphere. In the hunt for alien life, that kind of chemical literacy could be the equivalent of reading a newspaper. Then there is electricity and magnetism. Moving salty water through a planetary magnetic field induces electric fields. It should be noted that many Earth species already sense this. On K218b, with powerful currents and a thick, conducting ocean, electric and magnetic senses might be as basic as hearing is to us, giving a built-in map of direction, depth, and even weather far overhead. Cognition in such a world might feel strangely calm to us, with a close but cool star and a relatively gentle Goldilocks zone orbit. There may be fewer sharp day-night cycles, fewer dramatic seasons. So intelligent life could evolve around long, continuous rhythms rather than frantic days and nights. Activity and rest might flow like tides. Slow pulses of thought, memory, and planning stretching over many of our days. Would such minds even understand our obsession with minutes and deadlines? Communication would follow the medium. In the ocean, flashes of bioluminescence could form complex visual languages, not just simple glows. Patterns of color, intensity, and timing might encode grammar the way our voices encode tone. Pressure pulses, carefully shaped waves, could travel for kilometers as spoken sentences. Higher up, in the atmosphere, intelligent drifters might modulate tiny jets of gas, releasing plumes of different chemistry as signals like scented radio. Pattern interrupt. What if, to them, sound is primitive, but chemistry is poetry? Optimistically speaking, such languages could carry layers of meaning we struggle to imagine. One channel in pressure, one in light, one in scent, all at once. Their information structures might be more like chords than single notes. And here is the philosophical twist. If a being from K218b ever looked up at its dim red sun through a comforting, thick hydrogen atmosphere, would it see a harsh, alien world or home? So it's time to find out the truth about our own bias. From their perspective, Earth, with its blinding blue daylight, razor-thin air, violent seasons, and brutally sharp shadows, might seem not just extreme, but utterly uninhabitable. In the hunt for alien life, that may be the most important lesson K218b can teach us. Normal is always local. So if minds like these exist, how would we ever recognize their technology, their cities, their impact on the planet itself? That is where we turn next. Hycean worlds versus Earth twins, rethinking the Goldilocks zone. If normal is always local, then here's the uncomfortable question. Have we been looking for the wrong kind of normal all along? For decades, we treated planets like Earth as the gold standard. But what if the most common homes for life in the universe are not Earth twins at all, but swollen ocean worlds wrapped in hydrogen skies? Traditionally, in the hunt for alien life, we have chased a very specific dream. We wanted rocky, Earth-sized planets with thin atmospheres, blue surface oceans, and continents where chemistry could play out in familiar ways. The classic Goldilocks zone was drawn with these worlds in mind. Not too hot, not too cold, just right for liquid water on a solid surface. It felt safe because it looked like home. But while that picture is comforting, the data have been quietly rebelling. When we survey exoplanet systems, we do not see Earth clones everywhere. We see sub-Neptunes and mini-Neptunes, planets 2 or 3 times Earth's size with thick envelopes of gas, turning up again and again. This means the average habitable planet may not be a pale blue dot, but a Hycean world, hydrogen-rich atmosphere, deep global ocean, no land at all. Why does hydrogen matter so much? A hydrogen-rich atmosphere is incredibly effective at trapping heat. It should be noted that even a relatively faint red dwarf star can keep an ocean liquid beneath such a blanket at distances where an Earth-like atmosphere would freeze solid. That same thickness can smooth out temperature extremes, protect against flares, and even make tidally locked planets, permanently showing one face to their star, far more stable than we once feared. Of course, there are trade-offs. A Hycean ocean could stay habitable for billions of years, offering a calm, chemically rich environment for microbes and simple multicellular life. But without continents, tidal pools, or exposed rock, do you still get the same evolutionary pressure toward complex, tool-using intelligence? How do you build fire, metal, or electronics at the bottom of a high-pressure, dimly lit sea? Optimistically speaking, technology might still arise, but it could look so alien that we barely recognize it. Statistically, though, these worlds are hard to ignore. Sub-Neptunes are among the most common types of planet we have found. If even a modest fraction of them host Hycean conditions, they could outnumber truly Earth-like habitable planets by a wide margin. So it's time to find out the truth. Is Earth the rule or the exception? K218b sits right at the center of this shift. It orbits in the habitable zone of its red dwarf star, shows hints of a hydrogen-rich atmosphere and possible water vapor, and may be our first real Hycean candidate. How we interpret this one planet will decide which worlds we point our next telescopes at, and which strange biosignatures we dare to search for next. What if they're already there? Civilizations on ocean giants. If K218b really is a Hycean world, we have to ask an uncomfortable question. What if something out there has already claimed those oceans? Because once a planet offers stable energy, chemistry, and time, evolution tends to get ambitious. On an ocean giant, the path to intelligence would not begin with fire and stone. It would begin with social minds in the water. Picture long-lived, highly communicative creatures, more like a fusion of dolphins, octopus, and coral than anything on Earth. They might form pods or clustered colonies, using complex sound, color changes, or even pressure waves through the water as language. In the hunt for alien life, this kind of rich, three-dimensional communication network is exactly the sort of thing we expect to give natural selection a reason to favor bigger brains. But how do you build technology in a world with no dry land, no easy metals, and no campfires? This means any advanced civilization on K218b would have to hack the rules we take for granted. Instead of mining rock, they could harvest buoyant materials from their own biosphere, gas-filled bladders, tough organic shells, forests of floating, balloon-like organisms. Ice layers at depth, or near the cool upper ocean, might become their scaffolding, carved and fused into vast arches and domes. Biologically grown structures, living bridges, signal towers, or nutrient factories could replace our concrete and steel. Without fire, chemistry changes. It should be noted that many reactions we drive with flames can also be powered by electricity, pressure, or catalysts. So imagine them domesticating lightning in miniature. Controlled electrical discharges pulsing through conductive gels used to refine compounds or store energy. Geothermal vents on the seafloor could act as natural reactors, where they guide hot fluids through engineered channels to power their cities. Optimistically speaking, they might even practice deliberate biological engineering, shaping symbiotic microbes to produce plastics, fibers, or light on demand. But would such a species ever look up? On K218b, a thick hydrogen atmosphere and cloud decks could hide the wider universe almost completely. Starlight from the red dwarf would filter down as a dim, reddish glow. The stars might appear only rarely, through fleeting gaps, as strange points flickering above the waves. So let's begin to imagine an astronomy born not from gazing at a clear night sky, but from subtle changes in tides, in radiation levels, in the heartbeat of their star, felt through the ocean. Their curiosity about the cosmos might arrive late, but when it arrives, it could be intense. If such a civilization reshaped their planet, what would we actually see from here? We would never resolve their cities. Instead, we would hunt for fingerprints in the atmosphere, chemical imbalances that do not fit geology alone, strange combinations of gases, or heat patterns that suggest large-scale energy use. Artificial radio emissions could, in principle, leak out through the hydrogen envelope and ride the interstellar dark to our telescopes. So it's time to find out the truth. If someone is already there, would JWST's spectra whisper their presence in those methane and CO2 lines? Or would an entire thinking ocean remain silent to us, hidden just beyond the edge of our data as we move on to the next planet? From K218b back to us, what this world tells us about life. If there is a thinking ocean under that hydrogen sky, what does that world really tell us about life and about us? To answer that, we need to step back and look at what makes K218b so special. This is a planet circling a relatively calm red dwarf star in Leo, about 124 light-years away. Its orbit keeps it in the Goldilocks zone, where temperatures could allow liquid water. Above, JWST sees a thick, hydrogen-rich atmosphere laced with water vapor, methane, and CO2. Below, the best models point to a deep global ocean wrapped around a world larger and heavier than Earth, but still potentially habitable. In the hunt for alien life, that combination is revolutionary. We grew up thinking that the right planet had to look Earth-like. Continents, a thin nitrogen-oxygen atmosphere, blue skies, and a bright yellow star. But while Earth is our only confirmed example, K218b whispers that this might just be one way to do biology. This means life might also flourish under red suns, beneath hazy, steamy skies, on planets where there is no land at all, only endless water and crushing air. So let's begin to challenge our instincts. Do you really need shorelines and shallow seas for chemistry to organize into cells? Or could microbes drift in high clouds of a hydrogen atmosphere, feeding on faint starlight and chemical gradients? It should be noted that even on Earth, some of the most robust ecosystems live in deep oceans and dark hydrothermal vents, far from sunlight and continents. K218b simply takes that idea and scales it up to a whole planet. Here is where probability enters the story. Sub-Neptunes and mini-Neptunes, like K218b, are among the most common types of planet we have found in the galaxy. If even a fraction of them turn out to be Hycean worlds, hydrogen-wrapped oceans in the habitable zone, then the real estate for simple microbial life in the universe expands dramatically. Optimistically speaking, every time we add a new class of potentially habitable world, the odds that life has emerged somewhere else tick upward. But while this picture is exciting, our ignorance is still enormous. We do not know whether K218b is a sterile water world, cleansed of complexity by pressure and chemistry, or a thriving biosphere reshaping its atmosphere. JWST's spectra are detailed, but they are still just thin lines of data crossing our screens. Each new observation narrows the range of possibilities, yet the crucial question, life or no life, remains open. So it's time to find out the truth in a different way. Instead of only asking, are we alone, in some vague cosmic sense, We are now forced to ask, what kinds of strange, beautiful, alien environments might life call home? Could a dim, red dwarf system with a swollen, steamy planet like K2-18b be one of them? And if the answer is yes there, where else should we look next? And what signatures will we dare to claim as the first real evidence of a living alien world? The next observations, how we'll test the Hycean dream. So if K2-18b might be a Hycean world, how do we actually prove it? In the hunt for alien life, hints are exciting, but astronomy only moves from myth to reality when those hints survive brutal, repeated testing. This means our first task is simple to say and very hard to do. Watch K2-18b again, and again, and again. JWST has already captured a few precious transits, when the planet slides across the face of its red dwarf star and some starlight filters through its atmosphere. The next observing campaigns will stack more of these transits, using different instruments and wavelength ranges to push the signal-to-noise higher. Are the water, methane, and CO2 features really as strong as they looked at first? Does that tentative dimethyl sulfide blip stay put, or does it fade into the noise when we collect cleaner data? It should be noted that JWST is only the beginning. Over the next decade, enormous ground-based observatories, like the extremely large telescope in Chile, will train their segmented mirrors on Hycean candidates. From the ground, they can tease out higher resolution spectra, separating narrow absorption lines in the atmosphere into finer detail. In parallel, future space missions, such as the planned Habitable Worlds Observatory, are being designed with one goal in mind: directly studying the atmospheres of small, potentially habitable planets, including sub-Neptunes that sit in the Goldilocks zone of their stars. What exactly are we looking for in all this? Beyond simply confirming water vapor, astronomers want precise ratios of methane, CO2, and hydrogen because those control temperature and pressure at the possible ocean surface. We will search for additional molecules like ammonia and nitrous oxide, which on Earth can be associated with biology, but can also emerge from purely geological processes. So it's time to find out the truth by tracking how these gases change with time. Do we see seasonal patterns as K2-18b orbits its star? Subtle shifts that repeat could hint at climate cycles, or something more intriguing. But while K2-18b is the current celebrity, it cannot stand alone. Optimistically speaking, the real power of JWST and its successors will come from comparative planetology. By surveying dozens of sub-Neptunes and Hycean candidates around different red dwarfs, we can ask, is a hydrogen-rich, water-bearing atmosphere common, or is K2-18b an outlier in a mostly barren population? If several planets show similar atmospheric chemistry, then K2-18b might be just one member of a vast new class of potentially habitable worlds. And if they do not, then K2-18b becomes either a rare jewel or a cautionary tale about how easily we can misread alien skies. The story of this distant planet is only in its first chapter. The next decade of observations could transform it from a tantalizing maybe into our first real example of a life-supporting ocean world, or reveal just how tricky and deceptive exoplanet atmospheres can be. If you stepped on to K2-18b tomorrow, a final thought experiment. So let's begin where all of this speculation becomes personal. If K2-18b really is a Hycean world, what would it feel like to arrive there yourself tomorrow? You descend from orbit inside a small lander, leaving the black vacuum and slipping into a swollen halo of gas around the planet. Outside the window, the red dwarf star of this system shrinks and deepens in color, its light filtered by a hydrogen-rich atmosphere that stretches far above any putative ocean. At first, the view is bright, almost gentle, but while the upper layers are thin and transparent, the clouds below are not. As you drop, the sky darkens from pale salmon to a deep, bruised crimson, and the glow of the star becomes more like sunset than midday. Pressure climbs. The instruments read values far beyond Earth's sea level, yet your cabin remains calm as the lander automatically levels out at a carefully chosen layer. This means you are entering the band where temperatures might be close to habitable, where liquid water could exist far below, and the chemistry JWST hinted at could actually play out. The clouds thicken into a continuous sheet. For a moment, you are flying through total red fog. Then you break into a clearing, a vast, engineered platform floating in the mid-atmosphere, anchored by balloons swollen with hydrogen and helium. When you step into the habitat's airlock, gravity hits you like a subtle but undeniable weight. K2-18b's mass means you now feel almost twice as heavy as on Earth. Every movement is deliberate. Every step reminds you this is not an Earth-like planet, no matter how welcoming the temperature gauge looks. Outside the structure, the wind never stops. It should be noted that models suggest hundreds of kilometers per hour in some jets, more like a permanent jet stream than a passing storm. You hear it as a distant, continuous roar through the hull. Through thick, reinforced windows, you walk to the edge and look out. Below you, there is no land. Only an endless, dark ocean disappears into orange-red haze, its surface barely visible through scattered breaks in the clouds. Above, layered decks of vapor stack towards space, glowing faintly with scattered red light. Occasionally, entire regions flash from within as lightning rips through hydrogen-rich storms, illuminating columns of cloud that stretch for tens or hundreds of kilometers. In the hunt for alien life, this is where the scene becomes truly strange. As twilight deepens, faint bioluminescent flickers appear far below, like distant cities under the waves, rising and fading in slow pulses. Are they chemical reactions in the water, or something more organized? Higher up, you spot vague shapes drifting within the clouds, bright on thermal cameras, but nearly invisible to the eye. Perhaps balloon-like structures riding vertical currents. Your suit's chemical sensors quietly collect data. Methane and carbon dioxide are there, as JWST reported. Optimistically speaking, tiny spikes of dimethyl sulfide appear in the readout as well, right on the edge of certainty. On Earth, almost all of it comes from marine life. Here, it could be a false alarm, or the first whisper of a global biosphere hidden beneath the clouds. So it's time to find out the truth, at least in your imagination. You pull back in your mind's eye, from one human standing on a fragile platform in an alien sky, to the full disk of K2-18b, wrapped in storms, lit by its dim, red dwarf star. Then farther still, to a galaxy where red dwarfs are common, and Hycean worlds might outnumber Earth-like planets. If this one world can almost fool us, from 124 light-years away, how many others are hiding their own oceans, their own chemistries, their own versions of life behind deceptive atmospheres? And if K2-18b is only the first hint, what happens when we finally point our telescopes at its true siblings, and the signals in their skies refuse to be explained away? What K2-18b teaches us about ourselves: if one strange, distant planet can do all of that from 124 light-years away, what does it do to us, right here on Earth? We started with a faint red dwarf in Leo, a modest star with a small, tight Goldilocks zone, and a world, K2-18b, orbiting in that delicate band where liquid water might exist. From there, we followed the Hycean hypothesis, this bold idea that a planet larger than Earth, wrapped in hydrogen, could still be habitable. We watched as JWST split its starlight and delivered an atmospheric verdict: water vapor, methane, carbon dioxide, and hints that the atmosphere is not the thick, suffocating shroud of a dead mini-Neptune, but something more subtle. This means we could be looking at an ocean-bearing world under a hydrogen sky, Once that door opened, imagination rushed through. We pictured dim red daylight filtering through clouds, a global sea heaving under stronger gravity, strange weather patterns in a deep atmosphere, and ecosystems that might use red light instead of yellow. We even asked what it would feel like for humans to live there, in floating cities or high platforms, sheltered from crushing pressure, looking down into an alien ocean that might or might not host life. In the hunt for alien life, K218b gives us a crucial scientific lesson. Habitable does not have to mean Earth-like. It should be noted that for decades we focused on rocky twins, blue marbles with nitrogen skies and familiar continents. But while Earth is our only confirmed example, K218b reminds us that the universe may prefer other templates, Hycean worlds, steam-wrapped oceans, and planets where hydrogen, not nitrogen, sets the stage for chemistry. Here is the pattern interrupt. Maybe we are the weird ones. We walk around assuming our atmosphere, our blue daylight, our single moon, are normal. Yet next to red dwarfs with tight, crowded systems, Earth and the Sun start to look like an unusual experiment. Our planet is not the standard of habitability. It is just one solution among many that physics and chemistry have tried. Emotionally, that does something to us. Imagining life breathing under a hydrogen sky forces us to ask, how adaptable is life, really? How fragile is our own environment by comparison? Optimistically speaking, it suggests that biology might flourish in places we once wrote off, but it also underlines how contingent our comforts are. Our breathable air, our stable temperatures, our familiar daylight. So it's time to find out the truth about what this means for us. If one world around a distant red dwarf can reshape how we think about planets, stars, and life itself, then staying curious about discoveries like K218b is not just entertainment. It is part of how we, as a species, wake up to our real place in the universe and decide what we do with it next. Your turn. Would you visit a Hycean world? So let's begin with a simple question that is anything but simple. If distance were no object, if we could step through a portal tomorrow, would you actually choose to visit K218b? Imagine it clearly for a moment. A planet wrapped in a hydrogen-rich atmosphere, orbiting deep in the Goldilocks zone of a dim red dwarf star, with an ocean that may never end. No continents, no familiar blue sky, just a soft red light filtering down through thick clouds, and a sea that could hide pressures and temperatures far beyond anything on Earth. In the hunt for alien life, this is not the postcard Earth-like world most people picture. But it might be where the first real evidence appears. So which would you pick for your first interstellar trip? A Hycean world like K218b, under a crimson sun and a swollen sky? A tidally locked planet with one side frozen in darkness, one side blazing, and you living forever in the narrow twilight band between? Or would you wait for the comfort of a classic, Earth-like exoplanet, with continents, blue daylight, and clouds that behave in ways we instinctively understand? Tell us, clearly, in the comments, which environment would you rather explore first, and why? It should be noted that there is no safe option here. Every one of these planets would challenge our technology, our biology, and our imagination. This means your answer is really about what kind of mystery pulls you most. Is it the deep alien ocean of K218b? The eternal sunset of a tidally locked world? Or the eerie familiarity of a distant Earth twin that is almost like home, but not quite? We would like you to take this discussion beyond this video as well. Share this with a friend who loves science fiction, or who cannot stop talking about JWST and exoplanets. Ask them what kind of life they think is most likely on K218b, if any exists at all. Floating microbial mats feeding on faint red light? Chemically powered ecosystems far below the surface? Or nothing but sterile clouds and dark, crushing water? Optimistically speaking, debating these possibilities is part of how we prepare ourselves for the moment the data become unambiguous. Because this is only the beginning of our travel guide to the galaxy. In future episodes, we will dive into lava worlds with molten horizons, rogue planets drifting between stars in endless night, and super Earths where gravity reshapes oceans, mountains, and perhaps even biology itself. So it's time to find out the truth about how each of these extreme environments might feel to visit, and which of them could still be surprisingly habitable. And as you watch this, remember, right now, photons from the K2-18 system are streaming into the James Webb Space Telescope. Each spectrum is a message from that distant ocean world, carrying clues about its atmosphere, its chemistry, and maybe even its potential for life. We are only just learning how to read those messages. Stay curious. Add your voice to the discussion below, and we will keep exploring these strange new worlds together.